Electrophiles means those who are having attraction towards negatively charged particles, hence it will be either positively charged or neutral. So if I need a CH3 group in place of hydrogen, my alkyl group which I am taking, it must be CH3. The carbocation loses a proton to HSO4 minus to give the product Nitro Benzene. Hello everyone, this is Ambli Unnikrishnan from the Department of Chemistry. So today we are back with session 8 of the chapter Hydrocarbons. So in the last session we discussed about what is aromaticity and how we can predict the aromaticity or the conditions for aromaticity, right? Yes, based on Huckel's rule we discussed what is Huckel's rule, conditions for aromaticity. Then we started discussing about the methods of preparation of benzene as well as its physical properties, right? So in today's session we are going to study about the chemical properties of benzene, okay? So let's begin with the chemical properties. Benzene does not give reaction characteristic of unsaturated hydrocarbons. On the other hand, it is quite stable. We have already studied it is having extra stability, right? And gives substitution reactions. Due to the stability, right, they are undergoing substitution reaction or they prefer substitution reaction over addition reaction. Because of the high electron density on the ring, the electron deficient groups attack it with ease to give electrophilic substitution reactions. As the benzene ring is highly electron rich, it is electron rich, okay? The benzene ring, it is electron rich. So what happens? Electron deficient groups, right? Electron deficient groups are the ones which are having attraction towards the negative charge, that is positively charged. So, which is electrophiles, right? So, these electrophiles will come and substitute in the benzene ring. So, this is called as electrophilic substitution reaction. Some typical reactions given by benzene are electrophilic substitution reactions as well as addition reactions, okay? It gives addition reactions as well, but it prefers electrophilic substitution reaction. Why exactly electrophilic substitution? Because your benzene ring is electron rich. And electrophilic means those who are electron deficient, right? Those groups who are electron deficient and who have attraction towards negative charge. So they must be positive charge or neutral, right? So let's see. First one, we are going to start with electrophilic substitution reactions. Then later we'll start with the additions. Okay. So the substitution of hydrogen atom of benzene ring by an electrophile is called as electrophilic substitution reaction. So we know what is the structure of benzene that we have already studied. Alternate double bonds you are having, and in each of this carbon atom, yes, you have one hydrogen atom each, right? So this is C6H6, right? So what happens here is in electrophilic substitution reaction, hydrogen atom of this benzene will be replaced by an electrophile, right? An electrophile. This is what is electrophilic substitution. Hydrogen atom will be substituted by an electrophile. Okay. What is an electrophile? You already know this. An electrophile is an electron deficient chemical species which can form a new bond by accepting an electron pair. It may be either neutral or positively charged. So either it will be positively charged or neutral. Okay. Why positively charged? Because they are having attraction towards negatively charged, right? Positive and negative have attraction. So in that way you can remember. So electrophiles means those who are having attraction towards negatively charged particles. Hence it will be either positively charged or neutral. Okay. So examples we can take NO2 plus. It is nitronium ion. Okay. So as you can see there is a positive charge. It will have attraction towards negatively charged. And another one is Br plus bromine. Cl plus. Then as you can see here SO3, it is sulfur trioxide. As you can see it is neutral. It is a neutral electrophile, but still it is acts as an electrophile. Next one is CH3 plus which is methyl carbocation. So all these are examples of electrophiles. So I hope you understood how electrophilic substitution reaction takes place. An electrophile will be substituting an hydrogen atom of the benzene. Okay. Now moving on to the first one. First electrophilic substitution reaction, which is nitration of benzene. So nitration means what? In that way itself you can remember nitration means which group will be substituted in NO2. Nitro group will be substituted in place of hydrogen. Okay. So benzene on heating with nitrating mixture. So what is nitrating mixture? It is a mixture of concentrated nitric acid and concentrated sulfuric acid. So this is also important. What is nitrating mixture? It's a mixture of concentrated nitric acid and sulfuric acid gives Nitro Benzene. And this reaction is known as nitration of benzene. So what happens here? Hydrogen atom of the benzene will be replaced by NO2. Okay. And what is the reagent that we are using? It's nitrating mixture, which is a mixture of nitric acid and sulfuric acid. So as you can see here on the benzene, one of the hydrogen atom will be replaced by NO2. So from where this NO2 is coming? HNO3 and H2SO4 you are taking. So what happens here? This HNO3 is written as OH and NO2. Okay, so together you can see that it's still HNO3, right? So it's just split it and written it. So what happens here? This NO2 will be substituted in place of hydrogen. So you will get nitrobenzene and water. So I hope that is clear. So now we are going to study about the mechanism. How is this reaction exactly happening? The mechanism of this reaction, let's understand. Okay, so first step is the formation of electrophile. Okay, so as we are studying about electrophilic substitution reactions, we need an electrophile, right? So the first step is the formation of this electrophile. In this case, which is the electrophile we need, it is NO2 plus, right? So let's see. Concentrated nitric acid reacts with concentrated sulfuric acid to give the electrophile NO2 plus. So the nitrating mixture, from that we are going to get the NO2 plus. Okay, our electrophile. So let's see. HNO3 is written here. OH and NO2 you can see. And here you can see the H2SO4. The two hydrogen is written separately and HSO4. Okay, it's basically H2SO4 itself. So what happens here? You can see NO2 plus. This bond will break and you will get NO2 plus, and then you can see H, 3H and 1O, that will form H3O plus, and two molecules of HSO4 minus will be formed, right? H2SO4 breaks into H plus and HSO4 minus, right? So you will get all these. So from where did you get the electrophile? Yeah, your electrophile is here. Okay, so this is the first step, which is the formation of electrophile. Now the second step is the electrophile, which is NO2 plus, attacks the molecule of benzene to give carbocation. Okay, it gives carbocation. Next step is this electrophile which is formed will attack on the benzene ring and form a carbocation. Okay, so you are already familiar with what is carbocation. So this is your benzene ring to which the NO2 plus is going to attack. So what happens here? Along this double bond, the NO2 group will come and attach. Okay, so already one hydrogen atom is also there, right? One hydrogen atom also there. That is what is represented here. So this NO2 is having a plus charge, the electrophile is having a plus charge, that will be present here. So this is the second step. Now what happens? The carbocation is stabilized by resonance. Okay, we have already studied resonance, and it is the resonance hybrid of the following resonance forms. Okay, so as you can see here, initially the double bonds are present here. Now what happens? If the double bond shifts here, okay, double bond shifts here, what happens? Yes, the positive charge will come in this position, which is the para position, right? Now the double bond shifts here, this double bond shifts here, you will get the next resonating structure. And again, if this shifts in this direction, what happens? You will get the final resonating structure, which is the first one we have already seen. So what happens? The stability or the compound will stabilize using resonance. So this is happening once the carbocation is formed. Now what happens? The carbocation, the third step is the carbocation loses a proton to HSO4 minus to give the product nitrobenzene. So this is what is happening. We have the carbocation now, which is stabilized by resonance. Now this carbocation, HSO4 minus is there. Right, what happens? We just need the NO2 here. You have one hydrogen here and you have one plus charge here and you have an NO2. We just need the NO2 there. So what happens? This H will be removed. And how it will be removed? It will get attached with the HSO4 minus. You have HSO4 minus and H plus, which will together form H2SO4, right? And only NO2 will remain here, which is the nitrobenzene. So this is the mechanism. So what is the mechanism? In the first step, electrophile will be formed. Now the electrophile will be attacking the benzene ring and forms a carbocation. And the third step, on the carbocation, hydrogen atom will be removed, that is removal of proton, and forms the nitrobenzene. So this is nitration of benzene. Moving on to the next one, halogenation of benzene. So what does halogenation means? We are going to substitute a halogen in place of hydrogen. That's it. Okay. So benzene on heating with the halogen in the presence of ferric chloride, FeCl3, or iron or iodine, catalyst gives halobenzene. So what happens again? On benzene, the hydrogen atom will be replaced by a halogen. So instead of H, you will get the X here. right? Any halogen will be replaced, okay? And what is remaining here? We are taking 2 atoms or 1 molecule of halogen. So, 1 X will be replaced here, and the hydrogen which is removed from here will combine with the next X, that is next halogen, and form hydrogen halide. I hope it is clear, okay? So, one example it is shown here. If we are adding chlorine, if you are going to substitute chlorine, that is chlorination we are doing, what happens? Cl2 we are going to add in presence of ferric chloride. So what happens? One Cl will be substituted here. The next Cl will form HCl here. What is that? You are going to get chlorobenzene. Instead of hydrogen, chlorine will be substituted. I hope that is clear. Now, next one is sulfonation of benzene. Okay, benzene on heating with concentrated sulfuric acid gives benzene sulfonic acid, and this is called as sulfonation of benzene. So using what we are going to do sulfonation? Concentrated sulfuric acid, again H2SO4 we are taking. Okay, so H2SO4, it is OH minus and SO3H plus. So what reaction we are studying here? Electrophilic substitution reaction, right? So which will be substituted here? This is the electrophile, SO3H plus. So that is what is shown here. So what happens? This SO3H plus will substitute in place of hydrogen, and you have one hydrogen here which will combine with OH and form water. Okay, so this is your product, which is benzene sulfonic acid. So you got your benzene sulfonic acid. Right, now the next one is alkylation of benzene by Friedel-Crafts reaction. By Friedel-Crafts reaction. So we are going to study alkylation as well as acylation here. Friedel-Crafts alkylation and Friedel-Crafts acylation, and the mechanism we are going to study. Okay, benzene on heating with monohaloalkane, that is alkyl halide, in the presence of anhydrous aluminum chloride, anhydrous AlCl3, aluminum chloride gives alkyl benzene, and this is called as Friedel-Crafts alkylation. So Friedel-Crafts alkylation means what? Yes, we are going to substitute an alkyl group in place of hydrogen, right? Nitration means nitro group. Yes, sulfonation, SO3H we have substituted. Then chlorination or bromination or halogenation, halogen group will be substituted. Same way, alkylation means alkyl group will be substituted here. So let's see, if we want alkyl group to be substituted, we are using an alkyl halide here. For example, let's take CH3Cl. This is an alkyl group with a halogen. So this is called as alkyl halide, right? So again, the same procedure. You have benzene here, right? And one hydrogen atom will be substituted by the alkyl group. And what happens? The hydrogen which is removed from here combines with the halogen and form HX. So what is that? You are going to get the alkyl benzene, the corresponding alkyl benzene that you are going to obtain. Okay. So now let's study the mechanism of alkylation. So the first step is again formation of electrophile. We need the electrophile R plus. Right, we are going to substitute what? The alkyl group. So that will be your electrophile. So first let us understand how this electrophile is formed. Okay, so the catalyst aluminum chloride, in presence of what this is happening? Anhydrous aluminum chloride, right? So the catalyst aluminum chloride combines with the molecule of haloalkane to give the electrophile. So as you can see here, aluminum chloride, okay, and what else we are having? Alkyl halide. Now this both will combine and forms AlCl3X minus. The halogen will be added there. And what else is there? R plus. Okay. And what else is there? R plus. You got your electrophile. Okay. The next step is again the electrophile is going to attack the benzene ring and form carbocation. It's similar to what we have studied in nitration. So first step, we got the electrophile. Now electrophile is going to attack the benzene ring and form carbocation. So the benzene ring, electrophile is coming and attaching here, it attacks here, and you will get the carbocation. In the next step, the carbocation is being stabilized using resonance. So resonance takes place here and the carbocation becomes stable. So if the bond shifts here, what happens? The positive charge can come here. If it shifts here, the positive charge will be here. And in this way, this is the resonance hybrid of it. So it is shown in this way means the double bond can be in either of these positions. So this is the resonance hybrid of all these structures. So through resonance, this will be stabilized, right? Now the third step is again what we have already studied, the carbocation which is formed now loses a hydrogen or loses a proton and forms the compound that we need. Okay, so the carbocation combines with AlCl3X minus Where did this AlCl3X minus come? It is from this first step. Okay, to give the products alkyl benzene and hydrogen halide, the catalyst AlCl3 is regenerated. So let's see how that is happening. So what is removed from here? Hydrogen atom or the proton is removed from here. So H plus will be removed. Okay, and that will combine with the X minus. We have H plus and X minus, which will form HX. What else is left here? AlCl3 we are getting. Now what was here actually? It is the alkyl group. So what is that you are going to get? You get the alkyl benzene as well as the hydrogen halide and AlCl3. So I hope that is clear. Now what we are going to study is conversion of benzene to toluene. One specific example we are going to take here. Toluene. Toluene means it is methyl benzene. Okay, that means on benzene you need to get CH3 group and methyl group. So this is called as toluene. So how can you convert from benzene to toluene? You have already studied alkylation of benzene, right? Friedel-Crafts alkylation. So if I need a CH3 group to be substituted in place of hydrogen, I need to take which alkyl halide? Yes, methyl chloride, right? CH3 Cl I have to take. Methyl group should be there so that it gets substituted. So benzene we are going to add methyl chloride in presence of anhydrous aluminum chloride, and what happens? CH3 group will be replaced here and you'll get HCl. Okay, so I hope that is clear. Now it involves the following steps. The first step is we are going to see the mechanism of it, and it's also quite similar to what we have already studied. First is the formation of CH3 plus. Okay, so how you are going to get that? AlCl3 is there. Okay, and you have your methyl chloride. What happens? This will combine and form AlCl3, AlCl4 minus, and you have CH3 plus, which is left here. So you got your electrophile. That's the first step. Next step, what it is, we have already studied. This electrophile is going to attack the benzene ring and form a carbocation. Right, that's the second step you can see. The CH3 is going to attack the benzene ring and you will get a carbocation. That's a second step. Now this carbocation will be stabilized by resonance. That's the next part. Okay, so what happens? It will undergo resonance and form the resonance hybrid here. Okay. Now the last step, what happens? Even this we have studied till now. The carbocation which is stabilized, what happens? Yes, it loses a proton H plus and forms the desired product. So the carbocation combines with aluminum chloride to give the product toluene and hydrogen chloride. The catalyst AlCl3 is regenerated. Just now we have studied this reaction. So what is that happening? H plus is removed. Right, it will combine with this, it will form HCl, right, and AlCl3 is regenerated, and what is left here? H plus is removed. You just have the CH3. That means you have the methyl benzene, that is toluene. So I hope that is clear. So in the next session, we are going to continue with few more chemical properties of benzene. We have discussed Friedel-Crafts alkylation here. Now we need to discuss Friedel-Crafts acylation as well as few more chemical properties, right? So I hope the topics we have covered in this session is clear for you. So that's all for today. Thank you.